Welcome to today's introduction video. Today we're going to talk about functions and about the main notation that is important when we're discussing functions. So this is again part of the introduction, and that section is called the functions. Now we're not going to formally introduce what a function actually is as a mathematical object. I assume you're familiar with the notion of functions from school. So we just sum up the notation at first. We'll say function. Let's call it f. That is an object that is described by the following. Consists of, first what we need is some set x that acts as input set for the function. Call that set the domain of the function. So an arbitrary set x called domain of f, and as I said, think of that as the input, the set of possible inputs of the function. Then on the other hand, we have a set of possible outputs of the function. And to make things a little easier, you usually don't just list the possible outputs, but you list some superset of that. And that is called the codomain. So some set, we call it y, called codomain of f. And that is a superset of the outputs of f. And then the most important part, of course, is a function takes one possible input value and transforms it to some possible output value. So there has to be some function value for each possible input x. How this is computed is a completely different question. You could just enumerate all possible function values. You could give some formula to compute the function values, or you could make some implicit or explicit description or some algorithmic approach to get the function value. All of this is valid. And if we're talking about a function in general, we do not care how this function value is actually defined. The important thing is for each input value, there must be exactly one output value. Okay, and that's the third part of a function, this definition. So for each x in the domain, capital X, a function value let's denote that by y in capital Y. And the usual notation for this, so this is usually denoted as y equals f of x. So f of x is the function value assigned to the input value x. Now for notation, so a function is usually denoted by giving these three descripting values in some way. The domain and the codomain are the easiest to define. So what you usually write is I have a function named f that maps from the domain x, and then you write an arrow to the codomain y. Right? So this defines name of the function, the domain, and also the codomain. And then next to that or below that, you somehow define the function values by either giving a formula, an enumeration, an implicit description, what the function does, whatever you want to do to define that assignment. Okay, this y equals f of x is sometimes also written as x maps to x. So that arrow would be pronounced as maps to. Yeah, meaning you assign to the input value x, you assign the output value f of x. As I said, the function values can be defined in many, many ways. So let's just write this down as well. The function values defined in many ways. For example, and this list is not exhaustive, so we could just enumerate them. Through enumeration, and you will usually do this for very small domains. So what I mean by that is explicitly writing down f of x for each possible input value. And of course, this is only possible if the set of possible inputs, if the domain can actually be enumerated or finite, can actually write down those possible functions. For infinite domain, or even for not enumerable domain, this is not an option anymore, obviously. So the one way that you're probably most familiar with is definition through an explicit formula. Take a formula that transforms the input value x somehow, and that gives you the output value. Okay, for example, it could be something like f of x equals x squared plus 7. Of course, that is possible even if the domain is infinite. Yeah, that's not a problem. Given some possible input value x, you know exactly how to transform it, how to compute the corresponding function value to it. And of course, there could also be an implicit description. Meaning the function value is the process of some algorithm or some other process. Even something that you might not be able to solve. You just have to know that there is a unique solution for that description to make that actually a function, but you don't have to give a procedure to how to solve that. One example for that, for example, could say something like, for each x in x, the value of f of x is the lowest prime number p with p greater or equal to x. So if x is a prime number, you take x itself. If not, then you just take the next prime number that comes after x. That is a unique definition. Each input has exactly one function value that's assigned to it. Several inputs will have the same function value, but that doesn't matter for a function definition. So that was also a possible way of assigning a value. Okay, so that much for the basics. Then there's some notation and some terms that are associated with functions, and let's quickly go through those. Some of those might again be familiar. Some might be new, depending on what you learned in school and what you didn't learn in school. We'll make use of those now and again. For more special cases of functions, I'll probably explain those again, but just so you have heard the notation. seen the notation already. Okay, so several things you need to know about a function. I already talked about the codomain. The codomain is a superset of the possible values that a function can take, usually because it's much easier to define a superset. You don't have to actually think about what values the function can take and what it can't take. In many cases, of course, you are interested in the actual values that can be assumed by a function. And that set of values that can actually be assumed is called the image of a function. So first definition here. The image denoted by m of f of a function f is the set of all function values that are actually assumed by f. So in more formal terms, the image of f is the set of all y in capital Y, so y is the codomain, such that there exists some x in the domain, capital X, with f of x equals y. And of course, the image of a function f is always a subset of the codomain y. They might be the same, but y could also be larger than the image. The second notion that you're probably familiar with as well is the graph of f. Graph, denoted simply by graph f, of a function f is the set defined in the following way. Well, it's a set of tuples that consist of a possible input value x and its corresponding function value f of x. You just form tuples, and you do that for all x in the domain, and that is the graph. Okay, so x value, if you want to, the input value on the left of the tuple, and the output value on the right of the tuple, f of x, and the points that you can form this way, that's called the graph of a function. You're most probably familiar with that. And now there's three properties that you might or might not be familiar with, that we frequently encounter and frequently investigate when we're talking about functions. And those are injectivity, surjectivity, and bijectivity. So let's quickly talk about those. First is injectivity. A function is called injective if it doesn't assume a function value more than once. Or in other words, different input values for the function also produce different output values. So that means each function value is also unique. And a function with that property is called injective. So the function is called injective if no function value is assumed more than once. Or more formally, for all possible inputs x1, x2 in the domain, with f of x1 equals f of x2, well, two inputs, x1, x2, and they have the same function value. Now, if no function value is assumed more than once, the only way this can happen is that actually we use the same input. x1 must be equal to x2. So this implies x1 is equal to x2. That's injectivity. Or alternatively, you could also start with different inputs. So if you say x1, x2 are different, then f of x1 is different from f of x2. The first description is usually easier to use in a proof, but of course the second one will do as well. Okay, so that is injectivity. The second property we talk about often is surjectivity. That's pretty natural. We've talked about the image already, and we've talked about the codomain, and I mentioned several times that the codomain is a superset of the image. They could be the same, but they don't have to be the same. Now, a function where the image is equal to the codomain is called surjective. So basically, every value in the codomain is actually a function value, is actually assumed by the function. That is a surjective. So, a function is called surjective if each value in the codomain is a function value. Or in other words, for each y in capital Y, there exists some x in the domain with f of x equals y. Or simply, the image of f is equal to y, the codomain. Okay, that is surjectivity. And finally, the nicest functions, so to say, are functions that are both injective and surjective. And because those are so important, they get a name of their own. And those functions are called bijective. A function is called bijective if it is both injective and surjective. Okay, before we close this section, let's take a look at a small example. So we take a function from an actual application. Suppose we're operating a small local gas power plant, and that power plant can produce any power between two given limits. Of course, 0 is the lower limit, and let's say something like 5 megawatts is the upper limit for any given time. The production, so running the plant, of course, induces some cost. And that cost is a function of the desired output. So let's write this down first. Suppose a small local gas power plant can produce any power output between 0 and let's say 5. That is megawatts, 5 megawatts, yeah? And this production incurs a cost. The production cost is a function of the desired output. And let's say that function, let's call it C for cost. That's defined in the following way. The input is some value between 0 and 5, both limits inclusive. And the output is a cost, so it's a real number, and it shouldn't be negative, right? A cost is not negative, but it might be 0. So that is the codomain of that function. And let's define the cost function in the following way. Let's say, of course, if we don't produce anything, there'll be no cost. And I know that's a simplification because having the power plant available might also incur some costs as well. But let's simplify it for the moment to that. No production doesn't mean no cost. So it's 0 or x equals 0. And now once we start production, let's say there's two parts to that cost. There's a fixed cost that is incurred whenever the plant is running. And then there's a variable cost that depends on the desired output. So something like, let's just say 5, that's the fixed cost, plus 2x. Right? So that is for x in the rest of the domain, 0 to 5 and 0 excluded. Okay, so what we have is something like a fixed cost for production and a variable cost for production. Okay, now let's see about the properties of that function. First, I already mentioned the domain and the codomain of that function. Easy to see. So the domain here is simply the set 0 to 5, this interval. The codomain is equally easy. That is r greater or equal to 0. Now what about the image? Of course, you can imagine the image is not equal to the codomain in this case. A cost of 0 is totally possible. So the image of f, cost of 0 is possible. So 0 is contained in the image. Once we start production with a non-negative x, then we have to pay this value of 5 for the production cost. So anything between 0 and 5 is not possible. And also 5 itself is not possible because that would mean adding 0 variable cost, right? So the next possible cost is 5, and that's excluded. Anything above 5 is fine. The maximum cost we could incur, of course, is incurred at maximum production. So if we produce 5 megawatts of output, then we have 5 for the fixed cost plus 2 times 5 for the variable cost part. That's 15. Goes up to 15, and 15 is included. Okay, so this is the image of the function. Now, is this function injective and or surjective? Well, it sure is not surjective. No. Because obviously the codomain, that is r greater or equal to 0, is not equal to the image. For example, to prove that point, 1 is not included in the image. So if I'm asking you to show that a function is not surjective or is surjective, then please always give a concrete example. If you want to prove it's not surjective, just write down one possible function value that is in the codomain, but is not actually a function value. It's not assumed. And of course, you might have to prove that it's not assumed. In this case, it's easy to see because we have determined the image array. Now, what about injectivity? So, are there function values that are assumed more than once? And again, the answer is no. And let's see if we can prove this formally. So the function is injective. Okay, let's see. We start with two function inputs that are in the domain. So let x1, x2 be in 0 to 5. And let's assume we have picked x1, x2 such that their function values coincide. So f of x1 is equal to f of x2. Now we need to show that actually x1 is equal to x2. Nothing else can be. That's what we want to show. Because of the definition of that function, we have to make a case distinction here. Let's first look at the cases where at least one of those x's is 0. So if x1 is 0, that would mean f of x1 is 0. And of course, that would mean f of x2 is 0 as well, because values are the same. Well, a cost can only be 0 if the production is 0, so that means x2 is 0. And that in turn means x1 equals x2. And that's what we wanted to show. So in this case, we're good. If x2 equals 0, then of course the same thing happens. And now f of x2 is 0. That means f of x1 is equal to f of x2, so that's also 0. That can only happen if x1 is 0. And that means both x1 and x2 are the same. Finally, have a look at the last case, where we assume neither of those is 0. If x1 is not 0 and x2 is not 0 as well, then we know that f of x1 is equal to f of x2, and now we have a formula that we can use. So if x1 and x2 are not 0, then we can just use the formula for our function, that is 5 plus 2x1 equals 5 plus 2x2. Well, that's an equation that we can solve. Quality. Let's just subtract 5 on both sides first, and we get 2x1 equals 2x2. And then we can divide by 2. And that yields x1 is equal to x2. And again, that's what we wanted to show. So we have shown that our function is actually injective. So example for a function that is injective but not surjective. Not surjective. And that means the function is also not bijective. Okay, this concludes this little introduction to functions, to terms and definitions revolving around those. We'll see some more examples in the exercises, of course, but for now, that is enough, a general functions introduction. I'll see you in the next videos.